Okay, we're back here again talking some more about the central limit theorem. We already kind of looked through this a little bit earlier in the previous couple of videos, but we're going to talk a little bit more about that. Sometimes this is abbreviated CLT. It's a very important result in statistics. And one thing we noticed, the sampling distributions of the mean, or any statistic for that matter, have a distribution of their own that is different than the distribution of individual items. When you're talking specifically about the distribution of the sample means, it turns out that the center of it is the same as the center for the original population of individuals. So in other words, the mu of the x bar is the same as the mu of x. The mean of the means is the same as the mean of the individuals. But it turns out that samples are generally less variable than the group of individuals. So the variance of the sample means is the variance of the individuals divided by the size of the sample n. So increasing the sample size yields decreased standard deviation. And the standard deviation of the distribution of sample means has another name that we sometimes call it the standard error of the mean. So the sigma square of x bar is the sigma square of x divided by n, or more often we're just going to go right to the standard deviation. The standard deviation of the x bars is the standard deviation of the x's divided by square root of n. And this really doesn't depend on what kind of distribution we have. Okay. Now, if the distribution of individuals is actually normal, then the distribution of sample means is also normal. But it turns out the central limit theorem then tells us that the distribution of sample means from any underlying distribution of individual items approaches a normal distribution as the sample size gets larger. So the larger the sample size, the closer the distribution of sample means is to a normal distribution, even if the underlying distribution is very unlike a normal distribution. Once again, the mean of the distribution of sample means is the same as the mean of the individuals. Mu of x bar equals mu of x. The variance of sample means is the variance of individuals divided by the size of the sample. So sigma square of x bar is sigma square of x divided by n, which of course take the square root of that and you have the standard deviation of the x bars, or standard error of the mean. If the distribution of individuals is exactly normal, then the distribution of sample means is exactly normal regardless of the sample size. But if the distribution of individuals is highly non-normal, then it may take a larger sample size for the distribution of sample means to be approximated well by normal distribution, say over 30. So generally speaking, sort of our rule of thumb is if the sample size is over 30, then we don't really care. We don't worry too much about the underlying distribution. We will assume that the distribution of sample means is pretty close to a normal distribution. You can get by with a lot smaller than that if your data is pretty close to normal. So if the distribution of individuals is exactly normal, then the distribution of sample means is exactly normal. You don't have to worry about sample size. It could be even a sample size 2 or 3. If the distribution of individuals is unimodal, close to symmetric, and free of outliers, then distribution of sample means is approximately normal for reasonably small sample sizes, maybe as small as, say, 10. That's not any hard and fast number, but something in that ballpark. If it's also mound-shaped, then even better. Even smaller n's can work. For nearly any distribution, the distribution of sample means is approximately normal if the sample size is greater than 30. Now, if the distribution is highly skewed and has outliers, it may even take a larger than 30 sample size to make the distribution of sample means approximately normal. But the rule we're going to use in my class is if the sample size is greater than 30, we're not going to worry about the underlying distribution too much. We're going to assume that it will be that the distribution of x bar values will be approximated well by a normal distribution. And of course, what do we need to identify which normal distribution to use? We need its mean and standard deviation. And the mean that we use for that distribution of x bars is the same as the mean for the individual x's. And the standard deviation of the x bars is just equal to the standard deviation of the individual x's divided by the square root of the sample size. Now there are some demonstrations here online that you can try out. And I've got some screenshots for a couple of these that we might take a look at. For example, here we can take a uniform distribution like this, and here we have a normal distribution. Everything's been standardized here, so the mean of both of these is 0, and the standard deviation is both 1. So this is a standard normal. And notice as we take a larger n, that's not 2. It's just like a triangular distribution there, and then there it is, triangular. And then if I go a little bit bigger, let's see, there's 4, 5. So we're already starting to look pretty close to normal. And certainly once we get up to around 30-something, we're definitely looking normal. So it takes just a minute for a uniform approach, but it approaches pretty quickly. Here's an exponential. Okay, and of course this is actually not actually part of the graph. There's actually discontinuity there, but it looks something like this. Doesn't look too much at all like a normal there on the individuals, highly skewed. But here, even if we take a sample size 2, it's starting to a little bit more have a normal kind of shape. There's a sample of 5, size 5. Now it's starting to look more and more like the normal distribution, although the convergence is kind of slow on that one. Here we have a couple of normal distributions graphed. The first one is, I can control it with these parameters here. For example, I can shift it up a little bit, say to 5. And I can change the standard deviation. This is of the original distribution. Let's say if I go back to 3. So mean of 5, standard deviation of 3, that's the red graph. Now what we see on the green graph is the distribution of sample means with a sample size of 2. Notice it has the same center, which is 5 here, but it has a different standard deviation, which is this standard deviation. I say S, but I should have said sigma over square root of n, so that's 3 over square root of n for n equals 2. This works out to about 2.2 approximately, and we get that green graph. And so you can see what happens as we let the sample, see if I can get this to go up. Yeah, so if we let the sample size get larger and larger and larger, what happens? Well, that standard deviation is getting smaller and smaller and smaller. Notice the center has not changed. It's the same, but we get a higher and higher peak in the middle, lower and lower on the edges, so that we get more and more of the probability near the mean. That's a smaller and smaller and smaller standard deviation. Now, if we go back to here, I've got a link here, and if you go to this particular link, I found this out on the internet, and it's an applet that runs a simulation giving experimental data simulated where the population of individual has one of several choices, at least 4 choices there, of an underlying distribution. So this distribution is normal, or is uniform, excuse me, for the first one, which means all the bars should be the same height in theory, but in practice, of course, you'll see up and down from that somewhat. So here they did a sample, simulated this with computer technology, a sample of size 16,000, and looked at the mean and standard deviation here. It's uniform between 0 and 10, so the true mean is actually 5, and they approximated about 5.008, and there's the standard deviation of the samples that the sample that they pulled out. When we look at samples of size 2, it's actually a triangular distribution, and sure enough, that looks pretty close to a triangular distribution there. Okay, here's some more from a uniform distribution. This is this last one was samples of size 2. Samples of size 8 are drawn here. It's already looking a lot like a normal distribution. Here we resampled with samples of size 30, and now it looks extremely like a normal distribution. Here's a different distribution for the original one. It's skewed to the right, so kind of a high bar here, and then it kind of comes down. Samples of size 2 go up and back down, still skewed to the right, but looking more like a normal than the original one did. Samples of size 8 are better, looking a lot more like a normal distribution there. And by the time we get to 30, then you could definitely see the normal distribution looking a possibility there. Okay, let's look at another one. Here's another one. This is a bimodal, and it's high on both ends. In some ways, it's sort of the opposite of a normal. The normal, all the area, probability area, probability density is in the middle. This one, all the probability area is out to the edges. So it takes a little while for this one to get looking like normal. If we do distribution samples of size 2, we end up with this sort of trimodal looking thing here. Okay, samples of size 8, 4,000 samples, gives us something like this. Samples of size 30 with 4,000 samples gave us a graph looking like this last one. Okay, so those are done again from sample data. So those are big data samples, like 4,000 data points, and just seeing what happens experimentally. This is a lot like our experimental dice rolls from a couple of sections back. Now here are some theoretical ones. These are from that applet that I just showed you, these screenshots. So this is a normal distribution. I mean, the normal distributions in red. The in blue is the PDF for a uniform distribution. And then we have, for samples of size 2, 3, 4, 10, and 20, we see that as we get going, the distribution there of sample means is getting closer and closer to the distribution of a normal distribution. Okay, this is from an exponential distribution. These again are what we're looking at just a few minutes ago. Here's for n is 1. This is individuals. N is 2 looks something like this. Exponential. N equals 5 looks like this one here. N equals 10, 20, and 30. And so you see that again, as n gets bigger and bigger, it looks more and more like a standard normal. Here's some screenshots from what I just showed you just a minute ago. So once again, the central limit theorem says that the distribution of sample means has its own distribution. It has the same center as the distribution of individual values. It has a smaller standard deviation, specifically the old standard deviation of individuals divided by the square root of the sample size. And as we let that sample size get larger and larger and larger, then the distribution of a sample means gets closer and closer to a normal distribution.